Great. All right, excellent, everyone. So our next speaker here is Dr. David Reitzy. Dr. David Reitzy holds joint positions as the Executive Director of the LIGO Laboratory and a research professor at the California Institute of Technology. He obtained a PhD in physics from the University of Texas at Austin in 1990 and spent more than 20 years as a professor of physics at the University of Florida. His research interests focus on the development of ultra-sensitive gravitational wave detectors and just general gravitational wave astronomy. Reitzy was elected a Fellow of the American Physical Society, the U.S. Optical Society, and the American Association of the Advancement of Science. He was also awarded the National Academy of Sciences Award for a scientific discovery in 2017 for his leadership role in LIGO. He is a member and former spokesperson of the LIGO scientific collaboration that received numerous awards for the first direct detection of gravitational waves in 2015, including the Special Breakthrough Prize in Fundamental Physics, the Gruber Prize for Cosmology, and the American Astronomical Society Bruno Rossi Prize. He serves on numerous advisory committees from the international physics and astronomy communities, and we are so grateful and honored to have Dr. David Reitzy here with us today to talk about a field that is so exciting and someone from the collaboration itself. So without further ado, thank you so much, Dr. Reitzy, and we'll turn it over to you.
Okay, well, thank you very much. It's a delight to be here, even though we can't be doing this in person. I'm delighted to be able to talk to you from Pasadena, California. So let me make sure that I am projecting my screen. Can you see it? Yes? Great.
Yes.
Okay. Thank you. All right, so I've been asked to talk a little bit about gravitational waves, what they reveal about the universe and how we detect them. So for the next 45 minutes, that's what I will try and do. And I'll start at the beginning. And the beginning goes back about 100 years with Albert Einstein and the general theory of relativity, which is a really mathematically complex and elegant theory that Einstein came up with that basically explains gravity. It is the working theory in physics of gravity. Quite complex, makes lots of different predictions. It's sort of best summarized in a phrase that was coined by John Wheeler, another very eminent physicist, which says that basically space tells matter how to move, matter tells space how to curve. What does that mean? It means that I can think of two things. I can think of space, and Einstein also lumps time in that. There's space-time. And there's stuff, matter, energy. And when I put stuff into space, space changes shape. In other words, the geometry of space goes from something called Euclidean or Cartesian, if you will, in 2 dimensions to actually more complex kinds of geometries. And it actually warps the space, it curves the space. So one of the predictions, it took Einstein a while to actually get to the point where he believed it, was the prediction that as objects accelerate, as mass accelerates, they produce ripples in space-time. In other words, the geometry is dynamic. So any accelerating mass, any object, you wave your hand, you stop your car at a stoplight, you drop an apple, it produces a gravitational wave. The problem is the size of the phenomena. The amplitude of these waves is exceedingly tiny. So I'll go into a little bit more detail in the coming slides, but basically we like to think of these in terms of astrophysical objects, that you really need 2 big massive things colliding. In this case, it's black holes. So this little cartoon that I'm going to show you here is sort of a very, it's not really accurately physically, but it gives you the sense of what a gravitational wave is. As you have 2 objects, these are massive black holes, maybe about 10 times the mass of the sun, orbiting around one another. They're actually radiating gravitational waves. So that's that ripple that you see going across the geometric pond there. And as they collide, all right, they stop rippling. The reason their orbit is decaying is because they're actually producing these gravitational waves, and that's sucking energy out of the system. All right. Physically, it's a bit more easy to understand them if you look at this sort of geometry, and if you stare at it too long, you'll actually start to get cross-eyed or tired. So you might want to blink every now and then. But basically, a gravitational wave, if it were coming at the presentation, out of the presentation board to you, what it would be doing is it would be stretching space in one direction and at the same time compressing space. And what does that mean? It means literally that if I were to measure the distance between 2 points, those distances would be changes as a gravitational wave passes. And there are two polarizations of gravitational waves, much like light. You're familiar with in astronomy. So physically, though, they're strains. What is a strain? It's a change in length per unit length. So let me give you an illustration. So I can put an arbitrary coordinate system down, and so look at that left plot there. And as the x-arm contracts, that arrow sort of traces the total movement of the point as the gravitational wave stretches space there. All right, if I'm close to that crossing point, the origin of that coordinate system, you don't get much motion. But if I go further away, you get a lot more motion. So this is basically the idea behind detecting gravitational waves, is you want to basically make a measurement over as long a baseline as possible. So that's the L in that expression, delta L over L. Delta L is the change in distance that you're measuring over L, the distance. Okay, all right, so that's basically what we're trying to do here. Now for those two black hole cartoon, the cartoon that I just showed you, you can calculate what it is for black holes that are basically 10 times the mass of the sun. And they're hundreds of millions of light years away, roughly. The delta L over L that we're trying to measure is 10 to the minus 21, or 0.20 zeros with a 1 at the end of it. So these are really, really, really feeble phenomena. And it's actually deeply related to the fact that gravity is a very, very weak force. Okay, so all right, they're hard to detect. Einstein predicted them, maybe back in 1937. It's taken us a long time to get there and try and actually make these detections. But why do we do it? Why do we spend the time to do it? He actually thought they would not be detected. He did not think you could build devices that could detect them. Well, the reason a lot of people have spent a lot of time on this over the past 50 years is because they're really a new way to look at the universe. So it's detecting gravitational waves proves once again that Albert Einstein's general theory of relativity is right. That's all well and good. But really, they tell us things about the universe that other probes of the universe, such as photons that you measure in telescopes, or neutrinos, or subatomic particle collisions that you measure in particle colliders, can't give you that access to that information. So they're really completely new and unique probes of the cosmos. They're detectable gravitational waves, the ones that we can detect on Earth, are produced by really some of the most violent astrophysical events in the universe. When two black holes collide, it's actually there's a huge amount of energy that's released. They travel unimpeded through matter. Again, it has to do with the nature of gravity. It's a very weak force. It couples weakly to matter. So we don't have to worry about dust, in space. We don't have to worry about planets or stars or galaxies blocking gravitational waves. They just go right through it. They travel at the speed of light. We've actually proved that by doing a measurement, and they carry direct information about basically the relativistic motion of bulk matter, and that's really what you get out of gravitational waves. All right, so how do we do it? Well, we make devices called interferometers. Focus on the left picture for a minute. That is a very simple schematic of something called a Michelson Interferometer. The cylinder is going to be a source of light. In this case, it's a very pure source of light, a laser source. In the center of that sort of cross is something called a beam splitter. It takes the laser light, it splits it in two. The two sort of dark things that you see in the upper right and upper left are mirrors. They reflect the light back. The light comes back the same way it went out. It hits the beam splitter and it recombines. And depending on the relative lengths of the X and Y, the two arms, the two perpendicular arms, the light can either go back towards the laser or it can go towards that square, which is basically a light collector. So here's a cartoon of how that works. So the laser light goes out. We're going to color code the waves of the laser light in two different colors. The one going down the parallel arm, we'll call it the X arm, bounces back and recombines, hits the beam splitter. And let me see if I can stop it. So I'll stop it right now. And again, if we position the length of the arms, that's the distance between a beam splitter And one of the mirrors, and relatively the distance between the beam splitter and the other mirror, I'll call them the X and Y arm length differences, the light will basically destructively interfere. Light is a wave. It undergoes interference. It destructively interferes towards that plate that I show you, and it comes back towards the laser, which we don't show. However, if a gravitational wave passes, something a little bit different happens. So let me get the video going again. And as a gravitational wave passes, it's changing the distance between the beam splitter and the Y mirror and the beam splitter and the X mirror. So consequently, the amount of distance that the light travels changes, and that changes the interference pattern. Another way of saying it is we measure the time of flight of the light as it goes through. And so what we're doing here is basically by dynamically reading out that change as a gravitational wave passes, we can record a gravitational wave. So you can think really of an interferometer as a transducer. It takes basically these waves that are fluctuations in space, as I just showed you, reads them out using the time of flight of a laser down two different paths, and then turns it into basically, you can think of that black square there with the light on it as a photo detector, something you have in your iPhone or your Google phone or something like that. And it just reads out the light and it records the signal, and then it gets stored as voltage somewhere. So that's the concept. In practice, it's of course a lot more complicated, and we'll get into that in a minute. But the thing on the right is basically the Hanford Observatory. And you get a sense of scale there. I don't know how high that picture is taken from, but you can see I've drawn what the arm lengths are. So in this case, the X and the Y arms, those two, where the end mirrors are 4 kilometers from the beam splitter. The beam splitter is located in that big building in the lower right-hand corner. Okay, so that 4 kilometers in this case is the L in that expression delta L over L that I showed you. So you can then say, okay, well, I remember you told me that I need to measure 10 to the minus 21. You've told me what L is, it's 4 kilometers. So if you do some simple math, order of magnitude, that requires a delta L, measuring a displacement of about 10 to the minus 18 meters. All right, so, again, 0.17 zeros and a 1. All right, and to put that in perspective, that is take the diameter of a hydrogen atom, which is about 1 angstrom. All right, and divide that by 10 million. Alternatively, take the distance or take the diameter of a nucleus of an atom, a proton, for example, nucleus of a hydrogen atom, divide that by 10,000. So that's kind of the challenge that we're up against in trying to make gravitational wave detectors. I should point out, since for the astronomers, in astronomical optical astronomy, for example, it's all about aperture, right? You make the biggest mirrors that you can possibly make. Like, it's about light collection. Here, our equivalent in this case is the arm length. The longer the arms, the more sensitive our interferometer can be. So we actually made 2 of them. We have 2 of them. One is in Louisiana. That's the one on the left. The one in Hanford you saw, that's a different perspective. They're about 3,000 kilometers apart from one another. And there are very good reasons for making 2 of them. The first is really has to do with the fact that these interferometers are on the Earth. The Earth is a very noisy place. Lots of things shake, wiggle, change the characteristics of the interferometer. And so we want to make sure when we record a gravitational wave, it's a true gravitational wave and not some disruption that's local to one of the interferometers. So the signals we look for are always coincidence. And by moving things farther away, you get independent interferometers. So you're making sort of independent measurements of the same wave as it passes through the Earth. There's another reason that we have multiple interferometers, which I'll go into later. All right, so now this is probably the most technical slide that I'm going to show. What this tries to communicate is the kinds of physics that you need to understand in order to build a gravitational wave detector. So the plot on the right, a little bit complicated, but let's walk through it. On the x-axis is frequency. So this is frequency, like the frequency of sound, the frequency of light. In this case, the frequency goes from about 10 hertz to about maybe 5 or 6 kilohertz. All right. So this is the sensitivity range of our detectors. All right. So if you will, this is the collection bandwidth. And if you might recall that frequencies that we can hear, audible frequencies, are about 20 hertz to a few kilohertz also. So it just so happens that the gravitational wave detectors that we build are in tune, if you will, with the audio band, the human audio band. The y-axis is that quantity strain in somewhat funny units, but you get a sense of the magnitude of the measurement, 10 to the minus 22, 23. Now those curves there are all calculated curves that we calculate before we actually build and design an interferometer, understand what its capabilities are. And each one of those curves represents a different noise source, so we call them noise, that we have to understand and design either with or around or against to be able to build a gravitational wave detector. The black curve is ultimately the curve that is the curve we're trying to achieve when we make our detectors, right? And there are many different kinds of noises, but they sort of break down into three categories. The first are noises that basically change the length of the arm. All right, so the mirrors can get shaken. An easy one to understand there is, if you live in a place where there's a lot of trucks and the roads, or if you live in an earthquake zone, something like that. Seismic events or anthropogenic events, man-made events, can shake the mirrors. So you have to basically design a system that's robust against that. And the curve that you see, in this case, it's the brown curve, is our design curve for how we actually minimize that noise in our interferometer. Then there's some really funky noises. There's quantum noise having to do with the fundamental nature of light. Again, won't spend too much time on this, but basically light is photons. You can think about it as waves or photons. The photons carry momentum, and that momentum, when the photons hit the mirror, they impart that momentum to the mirror. Now, a photon is a tiny, tiny thing, and it has a little bit of momentum. But when there are lots of them, as we use in our interferometer, it actually can move the mirror. And the fact is that those photons don't all arrive in perfect unanimity and perfect sequence. They actually arrive a little bit randomly. That has to do with quantum mechanics. And then there's something called thermal noise. I'll explain a little bit what that is in the next slide here. The other kind of noises are sensing noises. Remember I told you that we measure the time of flight of the photon after it leaves, or the waves after they leave the beam splitter. There's also noises that can corrupt there. Basically, if there's any residual gas, if there are molecules, the light can scatter off the molecules. That changes the arrival time. The physical phenomena that you would know is index of refraction. So we try and make the index of refraction 1 in our detector. And then there's also correlated quantum noise called basically shot noise. And that has to do, again, the photons, when they arrive at the beam splitter and go to the detector, they arrive sort of at random times. And then there are also other hundreds of noise sources. So the ones we worry about, all right, the ones that dominate our detector, we worry about all of them, but the ones that dominate our detector are those that are shown in purple and in red. And I want to give, and the frequency dependence of all of them is all calculated and pretty well understood. But I wanted to give you sort of a physical intuition of the thermal noise. So here's a picture of one of our advanced LIGO mirrors. It's about 38 centimeters in diameter. It's about 18 centimeters thick. It's massive. It's 40 kilograms. And it looks beautiful, but it turns out that because it's at a finite temperature, and that noise that you hear actually reported by the detector as light hits the mirrors. Very, very tiny, but it actually, and shut it off so you don't have to listen to it, but it actually corrupts basically the light phase, and that leads to a noise source. So there's, like I said, lots of those, and we don't have time to walk through all of them, but I will sort of walk through the main pieces of the interferometer. We call it a detector, so you get the sense of it. So this is a more complex view. It's still a pretty simple view when you actually consider it against the real detector. But it's a pretty simple view of what the interferometer looks like, and in terms of all sort of the complexity of it. So there's the laser. The laser right now is about 50 watts. We're actually jacking it up to about 150 watts. There's a picture of it. You can see that it's actually it's actually the world's most stable laser. The people that work with it have to work in clean room garb. The laser power is high enough that it can actually damage mirrors if there's dust on the mirrors. Then there's a bunch of conditioning optics. Basically, the light out of a laser, even though it's very good, it's not good enough to actually put through the put into the detector to meet our requirements. So we have some conditioning. You see the beam splitter, you see what we call the end test masses. Those are the end mirrors that are 4 kilometers away. There are other mirrors, and those other mirrors, actually, the input test masses, what we call the signal and power recycling cavity, actually serve to amplify the signal inside the interferometer by keeping the light in there a lot longer. And then we have to condition the light that comes out. And that goes through something called an output mode cleaner, and then there are photodetectors. So this just walks you sort of through the key features. So this is one of the things we have to do, is beat the ground motion, the seismic motion, the fact that cars are driving around. So we have these very complex, actively controlled seismic isolation platforms. These things are very, really master classes in engineering that all of the optics sit on. Then there's the optics themselves. We talked about the mirror. The mirrors are actually suspended. The only contact that the mirror that actually reads out, that sees the gravitational wave that the laser bounces off on, that's that bottom mirror. It has actually it's contacting the rest of the world through 4 silica fibers. So these are basically homemade fibers. They're about 400 microns in diameter. So we actually suspend this 40 kilogram mass, this 40 kilogram mirror, off of those fibers. And the reason we do that has to do with some of the noises that I talked about earlier. Then there's the mirror themselves. That's a nice picture illuminating the mirror. Even though the mirror is not, perfectly shiny like you might expect a mirror that's doing optical astronomy, because in this case it's tuned to one particular wavelength. In our case, that wavelength is infrared. It's about 1064 nanometers, so a little bit outside the visible spectrum. So, and then we have to put it all in a vacuum system. Remember, I said molecules are bad. So we have the world's one of the world's largest high vacuum systems. So that's a picture of it under construction. Now it's all under those arches over there. It's a massive vacuum system. It's got 50 kilometers of welds, and I can tell you that building this vacuum system and maintaining it is really a tour de force. And of course, we need 2 of them, so there's one at each observatory. So that's sort of the components in the detector, the little bit of the physics behind the detector. If you put it all together, this is actually what we measure. And this is a very nice, you recognize the same axes, gravitational wave strain on Y, frequency on X. Obviously, and maybe I said this, maybe I didn't, but lower is better. Obviously, the lower that curve is, the more sensitive we are to gravitational waves. And you see there's some lines in it. Those lines are pretty well understood. So it's not perfect. It doesn't meet our modeling exactly. There's still some things we don't completely understand, particularly at low frequency, but it works, and it works quite well. So now let me shift into gravitational wave astrophysics. So let me start by coming back to this question of why do we build these big detectors, and why we spent so much time and intellectual energy on it. And the answer is because they can answer big questions. So one of the really first questions that one can ask, and it's probably one of the most challenging, is where does general relativity break down? General relativity is a theory that it is the theory of gravity. It has stood the test of time and experiment for 100 years. Might we see deviations from general relativity when we measure gravitational wave events? Perhaps. I would say it's unlikely, but you never know. More interesting, and again related also to general relativity, is what's the fundamental nature of a black hole? Black holes are very simple objects. They're basically characterized by 2 things: the amount of mass that they have inside them. In this case, it's not mass, it's actually the curvature of spacetime, and whether they have angular momentum, they're spinning. And black holes that just have mass and angular momentum, they're called bald. All right, but black holes may have other characteristics. They may be quantum in nature. There may be something beyond the event horizon where we can't see that would tell us that they're not exactly general relativistic black holes. They're something different. So that could be exciting if we could see something in our gravitational waves that shows that. How does matter behave under extreme conditions? We'll say more about this in a few slides, but basically when a certain kind of object, a neutron star, which is basically a remnant of a supernova explosion, about 1.4, 1.5 solar masses left behind, and as the name implied, it's made up mostly of neutron stars. They can also form in binary systems and pair off with one another, and they radiate gravitational waves, and they can collide. And when they collide at relativistic speeds. So these are really super big particle colliders in the universe. They're sort of neutron smashers. So you can study how the matter behaves under these very extreme conditions when they're moving at fractions of the speed of light. And there are different kinds of stars that have been neutron star types that have been predicted. None of them have been detected, but we look for these different kinds of stars. Another fundamental question, which I'll shed some light on later in the talk, is where do heavy elements come from? We know they come from the Big Bang, hydrogen and a little bit of helium. We know they come from supernova explosions, most of the medium atomic number elements. The heaviest ones, the lanthanides, actinides, they come, we believe until very recently that they came from the collision of two neutron stars, but you need to actually see a collision of two neutron stars to verify that. So again, we'll save a little bit more. How do stars explode? The physics of supernova is not completely well understood yet. There's lots that is understood. Models are quite predictive, but there's a part of the explosion, basically the reestablishment of a shock wave to blow off all that material that you see, that isn't well modeled. Could we find clues to dark matter and dark energy? Dark matter has been known for almost 80 years now, and it's still unknown as to composition. Dark energy, much more recent, only about 20 years old. Not much is known about that either. Could we see something in gravitational waves? And then perhaps the most exciting is what else is out there that we don't know about. When you build big new instruments, big new devices, perhaps you see things that you didn't anticipate. So how do you detect gravitational waves? So this is a cartoon. I'm going to skip the plot on the right in the interest of time, but remember I said that the Earth is a noisy place. So that plot that you see up in the upper left there, that's actually the noise, real noise from a gravitational wave. It's a time series, arbitrary units, but you can think of them as seconds. And that purple curve is a gravitational wave signal, hypothetical in this case, embedded in that curve. So if you were just to look, if I were to take the color away, you would not see that gravitational wave. You wouldn't, if the purple weren't there, if it were pink, you wouldn't see it. So let me actually show you how we do the detection. So we basically take a theoretical gravitational waveform, which we know how to calculate, and we cross-correlate it. And when it hits the real gravitational wave, this is called match filtering, we actually see a signal. So we have hundreds of thousands, and right now even millions of those different, we call them templates, that represent different masses of neutron stars and black holes that we search through every bit of our detector to detect gravitational waves. So this is a very computationally intensive event. The first gravitational wave, this is something that I will certainly remember for the rest of my life, was recorded on September 14th, 2015. The waves that you see there, the red one and the blue one in the lower plot, are actual waveforms that were recorded by in the red case, the Hanford detector, in the blue case, the Livingston detector, on the morning at the time when we detected the gravitational waves. A remarkable event. There's actually a tremendous amount of physical information contained in those waves. You can find the masses, you can find how far away the waveforms are. You can sense something about whether the individual black holes are actually spinning themselves. But we were able to take that data after we detected that, and we're actually, my colleague Kip Thorne and Saul Tucholsky and their students actually were able to use general relativity to make a visual simulation of what we saw. what produced these gravitational waves was two black holes, one about 36 times the mass of the sun, the other about 30 times the mass of the sun. And they were about 1.3 billion light years away. And so the movie that I'm going to show is actually a general relativistic visualization of the source of these gravitational waves. And I'll tell you that I've sped it up by about a factor of 100, or they have, the simulators. And what you see is these two gravitational waves going around. The background are basically stars for your frame of reference. The reason the stars are bending is because light is bending. Eventually these two black holes collide, and what's left is a big massive black hole. That whole event that I just showed you took about in real time about 0.2 of a second. During that time, about 3 solar masses of energy was converted from the black hole into gravitational waves. So this event, if you think about it in terms of luminosity, was a very bright event. Three times the mass of the sun was radiated away in that 0.2 seconds. Coming back to the point I made earlier about sound, if you play the signal just from the detector, you filter it a little bit, you hear that thump, thump, thump. I'll play it again. So that little thump, 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 I played it 3 times. There's only one actual recording of it, is the gravitational wave signal. So it's really amazing to think about the fact that these black holes, 1.3 billion light years away, they were moving at about 60% of the speed of light when they collided. The masses are 30 times the mass of the sun, produce this little blip that goes boop in our signal. So that sort of gives you a sense of how, at least for me, how really cool this astronomy is. So let me, in the last couple of minutes I have, talk about the other way we do gravitational wave astronomy, and that's that we partner with our friends and colleagues in the sort of electromagnetic astronomy community. So this idea that 2 binary neutron stars can collide, they produce gravitational waves. They also produce visual and infrared light. They produce radio waves, they produce cosmic rays, neutrinos, X-rays. Basically, they radiate across the electromagnetic spectrum. They radiate gravitational waves. And if you can see all of those things together, you get a really good picture, a really complete picture of what happens when 2 neutron stars collide. And I should point out that you might think these are rare events. It turns out that most stars in our galaxy, indeed in the universe, actually form in binary systems. Those stars evolve through their life cycles, depending on how massive the stars are. Some of them will just die away as white dwarfs. Some of them will go supernova and become neutron stars. Again, the mass is about 1.5 times the mass of the sun. The more massive ones will become black holes. And so these things are actually pretty ubiquitous. Just measuring them is quite challenging. So to do what we call GW astronomy, or multi-messenger astronomy, it's all about, as they say in real estate, location, location, location. A single observatory, the one in Livingston, the one at Hanford, we also partner with one in Virga in Louisiana, is insensitive to sky location. You can't tell where the signal came from, and that's because you don't have enough information. All you have is a waveform. But if you have a point source, like 2 neutron stars that are radiating gravitational waves, and you have at least 3 detectors, there's a subtlety which you can ask about if you're interested. By measuring the arrival time, the difference in arrival time between the signal at Hanford and Livingston, in this case in Italy, that gives you not great, but good information about where this event may have come from. And so the next big event, I mean, we detected a number of black hole mergers after we discovered the first one, but the next big event actually happened in 2017. This is just a picture of the network. The data I'm going to talk about is by those 3 gravitational wave network observatories. So the event that we saw in August, this was discovered the 17th of August in 2017. We recorded a signal, and again, I'll point you to the lower right. That's a different way of looking at our signals. We call it a spectrogram, or a time frequency plot. It plots time on the x-axis, frequency on the y-axis. And that track that you see going through there is actually the gravitational wave signal. All right. At the time, or soon after that signal came through our detector, it was also discovered completely independently in a different sector, in this case gamma rays and X-rays, by the Fermi gamma ray burst monitor detector, and also by the integral satellite detector. So these are satellites in space. Fermi is operated by NASA, integral by ESA. These events at the time were discovered independently. It turns out that they are actually highly correlated, and they come from the same event. And the event is the collision of two neutron stars. So let me see if I can get this video going for you. I don't know if you heard it. I certainly did. As they were getting close to one another, the closer they got, you started to hear a pitch, sort of a frequency pitch come up, and then it went whoop. All right, and that about the time they collided. And at the time they collided, because these neutron stars are made of neutrons, they have matter in them, the collisions are spectacular, and they produce these bursts of jets of gamma rays, jets of particles that come out. And so this single event produced both gamma rays and gravitational waves at the same time. Turns out it not only produced gamma rays and gravitational waves, as I said, it produced everything. It produced radio waves, optical waves. So we made an announcement. Actually, it took us about 3 hours in LIGO to discover, and Virgo to discover this. The gamma ray people had discovered it pretty quickly. All right, we both put out what are known as astronomical alerts, basically saying, hey, we have seen this event. And in our case, we had a location for it, as I'll show you. And the gamma ray burst people put out their alert saying, hey, we saw a correlated event at the same time. And that really lit the astronomical community on fire. And I believe about 75 major telescopes, as well as 7 or 8 satellites, actually went and tried to find this event. And this picture here just shows you the little green bananas are the things you should be focusing on. The smallest one is the error box. In other words, it's the location where we sort of pin down where this event might have come from. All right, now that's astronomically speaking not very good, but it's good enough for the astronomers to start going out and looking at different parts of that place. And so that's what they did. And we're going to zoom in, and what they found there are about 50 galaxies that are pretty close there. And they eventually zoomed in on this galaxy. This is in GC 4993, and it was identified as the source of the optical signal that accompanied the gamma ray burst and the gravitational wave signal. And the actual spectrum, this object that's encircled there, is the kilonova. It's the remnant behind the 2 neutron stars that have collided. And right now it's blue. It actually takes about a few days to actually turn red, infrared, and then it sort of just dims out and goes away. So all told, I think about 25 telescopes actually found this and looked at it, including the Hubble telescope. So it was really a very coordinated, it was probably one of the most coordinated astronomical observations in the history of astronomy. And without showing any of the data, I want to come back to this point that I made about nucleosynthesis. So it had been speculated, there have been theories that suggest that the elements that come in the lanthanide series, so the heavier elements, the ones down above sort of 40, 45 atomic number, are produced in the collisions of neutron stars. That was never known because we'd never actually observed one happening in real time. This event changed all that. And with that observation, you were able to actually extract, by looking at the optical spectra, this process of what's known as R process, rapid neutron capture nucleosynthesis. And it worked great. It worked exactly with the theory. So we can now say with confidence that a lot of the heavy elements, for example, the gold that you might have, uranium, platinum, are produced in these binary neutron star collisions. And so that was quite exciting. I'm going to wrap up with two more things. So first of all, we've been operating since 2015. We don't operate all the time. We actually are in a down period. Unfortunately, COVID has made us, it's taken a little longer than we had expected to get back online, but we're in the process of upgrading our detector. The reason we do that is the more sensitive it is, the more of these events we kind of see. So since we've actually been operating, we've had 3 observing runs since 2015. We've seen a total of 90 gravitational wave events. And in this plot, we call it the Eagle plot, sort of captures, in number, what kinds of event we've seen. So all those cyan curves are basically black holes that we have discovered. If you go up on the plot, those are the more massive. The higher you go, the more massive the black holes that we've seen. The guys in orange are neutron star collisions that we've seen. The guys that are hybrid, orange or cyan, we don't know what they are. They could be neutron stars, they could be black holes. So there's lots of interesting questions there. And just for perspective, the red and the yellow that you see sort of outlining the eagle at the bottom are neutron star collisions in the case of the yellow, black holes in the case of the red, that have been discovered through electromagnetic astronomy or radio astronomy. So we've really done, in just a few short years, we've learned a lot more about, for example, how many binary black hole systems are out there in the universe, what's their mass. There's still a lot more work to be done here, but it's really quite exciting. And that's where I'll wrap up, because now that we know that this field actually can produce great scientific results, we're thinking about what comes next. And there are 2 sort of very new, very big detectors that are on the sort of the drawing board. We call them 3rd generation gravitational wave observatories. So they basically, the one that I'm involved in is the one in the US. It's called Cosmic Explorer. It basically takes the concept of LIGO that I showed you earlier and just ups it by a factor of 10. So in this case, instead of having 4-kilometer arms, we have 40-kilometer arms. Sensitivity scales with the length of the arms, more sensitive. In Europe, they're building a really sophisticated design underground called the Einstein Telescope. It has 10-kilometer arms. Both of these detectors, once they get operational, and it will be 15 years, it'll probably be the mid to late 30s before they're operating, we'll be able to basically probe the entire star-forming universe. So they can look back so far in time, or so far in redshift in astronomical terms, that you can actually see black holes that were born very early in the universe, neutron stars that were born very early in the universe. So we'll be able to do a tremendous amount of gravitational wave astrophysics with these new devices. Sort of in coordination with all of this, there are other observatories that look for gravitational waves that are not exactly like LIGO and Virgo, because gravitational waves come in a spectrum, just like electromagnetic waves. Turns out you build different detectors to look for different regions of those spectrums. The ground-based detectors that I've talked about are the sort of the highest frequency events that you probably would see from an astrophysical perspective. So I call them the gamma rays of gravitational waves. But you go a little bit lower and you can see sort of massive black holes colliding, or even supermassive black holes colliding. And you can measure some of that using space-based detectors. There's a project called LISA, Laser Interferometer Space Antenna, that's going to go up in the next decade. There's also pulsar timing. That picture is of Arecibo, which unfortunately is no longer in operation. But there are other telescopes that can actually measure the arrival time of radio pulses and the information about the nature of black hole, the nature of gravitational waves at lower frequency, nanohertz frequencies, sits there. And then even the Big Bang itself actually, we believe, produced gravitational waves. So we can use gravitational waves to probe right back to the beginning of the universe. So sort of take it as a whole, this is just sort of, we think the beginning, or I think the beginning of gravitational astronomy. And I think the future is really quite bright. So I'll stop there. For more information, a couple of websites you can go to. And I have to gratefully acknowledge the National Science Foundation, who has faithfully supported us for the last 40 years, as well as my institution, Caltech, our partners at MIT, and also the much broader LIGO collaboration. So I'll stop there, and I'll be happy to take questions.
Great. So I will just read out some of the questions that were submitted through the Q&A portion of the Zoom call. So one question, let's see. All right, so here's a question. How can we specifically target different astronomical objects with LIGO? Is it similar to other telescopes where we can point it at certain parts of the sky, or would it be set to detect of signals from certain types of black holes?
Right. So yeah, this comes back to the reason why we have multiple detectors that all sort of operate at one. So the analogy that I can give is an interferometer is kind of like a microphone. No matter what direction the gravitational wave is coming in, like a microphone, no matter what direction the sound is coming from, it's going to get amplified or detected. All right, so that's why we need multiple gravitational wave detectors. And in fact, turns out the more you have, the more your accuracy is in detecting gravitational waves. We will never be as good as even the worst optical telescopes. The precision with which an optical telescope can resolve an object in the sky is measured in arc seconds. Ours are measured in tens of degrees, maybe a few degrees, depending on lots of things, which I won't go into. So we're very poor at that. But by having more of these detectors, we can move more. In terms of what kinds of signals that we can see, yes. So our detector is wideband, many spans many kilohertz. The signals themselves actually have a multi-band characteristic to them. In other words, as these gravitational waves are generated, the orbits are decaying, the objects speed up, and that actually changes the frequency of the gravitational wave. So it actually goes up as you get closer and closer to the merger. So we actually see broadband signals. There are other kinds of sources. For example, an isolated neutron star. There are reasons to believe that we could see gravitational waves from isolated neutron stars. They would produce a very different kind of signal, and we would know that because it would be a very monochromatic signal, or monofrequency signal. So by looking at the nature of the signal, we can tell what we're looking at.
Great. Okay. Next question is, it was similar to what you were talking about with extending the arm length, but it's, I guess, more getting into that. What if we increase the arm lengths from 4 kilometers to more than that? How precise will it get to detect gravitational waves? I guess it's like the degree of sensitivity increase.
Right. So great question. So sort of, I would say to first order. So sort of, if you think about nothing else, you increase the arm length by a factor of 2 or a factor of 5 or a factor of 10, you increase the sensitivity by a factor of 2 or 5 or 10. It's more complicated than that, because some of the noises that I showed in that complicated plot in the middle of the talk don't scale the same way as that simple factor of 2 or 5 or 10. Some get better, some get worse. So you have to actually do a little more. It's not just straightforward to make the detectors much longer, and there are more complications, and they have to do with just simple things like construction. So if you the Earth is, we don't notice it, but the Earth actually is curved, right? And if you ask yourself, if I have 2 points that are separated on the Earth by 40 kilometers, what's the arc and what's the distance between just basically a straight line connecting those 2 points and the arc that comes from the curvature of the Earth? And the answer is, if you go to the center, 20 kilometers midpoint, there's about 30 meters of height difference there. So you actually have to do a lot of earth moving. You have to actually dig, you have to basically make a trench that's 40 kilometers wide. You can be more clever about it, and we're trying to do that, but you can look for places where the curvature goes in the opposite direction. But you have to worry about that. The other thing that is more subtle, but is a problem, is that the mirrors themselves, as I said, are hanging. All right, and they're hanging with respect to the Earth's gravitational wave, or gravitational pull, or gravitational field. So as I go further and further away, the mirrors are no longer like this, but they're actually starting to open up because the angle opens up, and that has actually consequences that have to do with the noise. So there's a lot of thinking that needs to go. And to first order, you can say, yeah, we'll make it longer. Second order, you have to do a little bit more. And then the ultimate thing that always ends up limiting at some point is, how much money can you get to actually build these big detectors and vacuum systems. So lots of things in that seemingly simple question has actually got a lot of complexity to it.
Okay. Next question is, how does a different power laser used in LIGO change the instrument?
Right. So let me go back, and if I can. Okay. All right. Yeah. Let's look at this plot. So the two dominant noise sources that are due to laser power are what I call photon pressure at low frequencies, below, say, 50 or 60 hertz, and photon arrival time differences at high frequencies. It turns out they work against each other. If I want to I can turn up the laser power, and it turns out by turning up the laser power, I actually, the signal to noise, the signal that's recorded by the gravitational wave to the noise that comes from the photon arrival times, actually goes favorably as you go to higher power, because it's the square root of the power. So if I increase the power by a factor of 4, I would drop that noise curve by a factor of 2 on this plot. Unfortunately, that has the bad consequence of increasing the photon pressure by a factor of 2. Actually, maybe even 4. Yeah, it increases by a factor of 4. So there's sort of a sweet spot that has to do with how massive your mirror is. So if I have more if I turn the laser power up because I want better shot noise, that's the high frequency performance. I sacrifice some low frequency performance. The photon pressure curve goes up on the graph, but I can make a heavier mirror. All right, and maybe the heavier mirror is more resistant to the photon pressure. It turns out, so the simple answer is that we operate at about 150 watts because we think that's the sweet spot. Actually, we also have other problems with laser power that I didn't go into. The laser power is absorbed, even though it's not not much of it absorbed. So there are thermal effects in the instrument that we worry about. We've come up with a sort of a clever trick that's based on something called a Heisenberg uncertainty relation, that we can actually alter the characteristic of the light. We have a buzzword for it. We call it quantum engineering the light field, but that basically can actually both improve the sensitivity to high frequency by decreasing the random fluctuations from the photon arrival time, and also decrease the fluctuations from photon pressure just by a sort of a not so simple optical trick. So we can actually do a little bit better than both. But the simple answer is 100 watts, 150 watts is about what we can put into these interferometers now without actually causing serious problems.
Okay, I think we have time for a few more questions. 8:58 right now. Okay, next question. You had mentioned space-based interferometers earlier. This question asks, is a space-based interferometer feasible? And I guess that means whether physically, financially, et cetera.
Yeah, so the idea of putting an interferometer in space goes back probably 30, 35 years. And a part of the gravitational wave community has been working very actively on designing this concept called LISA. Go back and show you that picture. Get to it. There we go. So I don't know if you can see my pointer here. I can find it myself. Oops. There we go. Sorry. There. So this picture right here is actually an art. It's not exactly how LISA is going to be built, but the concept is very mature. The idea is that you send 3 different satellites in space. So this doesn't look like the interferometer, the L-shaped interferometer that I showed you. It's actually 3 interferometers in one. Each satellite is both a transmitter of laser light and a receiver. And the arms in this case are not 4 kilometers, they're 250 million kilometers. No, yeah, 2.5 million kilometers. Sorry, I get my distances wrong sometimes. So these, so they're very far apart. And they actually are not orbiting the Earth. They're actually in a solar orbit trailing the Earth. The technology for this has been demonstrated. There's actually been a mission that was very successful about 5 years ago, showing that you could launch one of these satellites and make the precision, the kind of measurement with the precision needed to be able to detect these lower frequency gravitational waves. So the name of the game now is to mature the design. The European Space Agency has already funded this and said that it will launch. They call it one of their large class missions. It will launch, I think right now in 2036 is the date that I remember hearing recently. NASA is getting involved in some of this. There's a lot of technology development that needs to be done. Doing things in space is hundreds of times more complicated than doing on Earth, because in this case you can't fix it if something goes broken. So there's a lot of work to be done. As far as the costs, because I heard that mentioned, I think right now it's, I want to say somewhere between 2 and 3 billion euros, but I don't remember exactly. So, but yes, it is. We believe it is very feasible.
Okay. Next question is a little more outside this talk, but I think it's still a good question. What advice would you give to someone in their undergraduate astronomy and physics degree who's interested in gravitational wave research?
Yeah, no, it's a good question. I guess I recommend a couple of things. First of all, there are lots of gravitational wave groups in the world now. Within the LIGO scientific collaboration, there's 100 of them, including in Canada. I don't think Toronto has one, but I know UBC has one. And I think there's one other university up there that has one. So first, do some research and look, to see if what you're interested in. And gravitational wave, astronomy comes in many different flavors. I happen to be a detector person. When I started in this, I started working on the laser and some of the optics for the detector. But there's also the people that actually look for the gravitational wave signals. That's computationally very heavy. There's people that think about the astrophysics and interpret them. So there are lots of different aspects to it. So there's lots of different opportunities. The second thing I would say is a lot of universities, including, for example, Caltech, have undergraduate research programs for summer students where you can apply. They're competitive, but you can apply. And if you get in, you'll come to Caltech, or sometimes we have students go to the observatories and do a project for a summer. And it's a meaningful project. It's often these projects get published as in the peer-reviewed literature. And a number of people that I actually know in the field, including a former student of mine, got started through one of these undergraduate research programs. So I would go online and do a lot of research about, are there programs that you might be interested in there? And if you want to go to graduate school, of course, look at the programs, that look at the schools that have good programs in gravitational physics and astronomy, and reach out to people there. I guess that's probably the best advice I could give.
How are we doing on time in terms of, because I have 2 more questions open, but if
I'm fine.
Great. Okay. Just didn't really want to. Okay. The next question is, seeing how the topic of gravitational wave detection is a relatively new subfield of astronomy, what are some pros and cons of working in this rapidly emerging field?
That's a great question. So let me start by expanding that question a little bit to say that gravitational wave astronomy is part of it. A lot of the work is also physics related, right? We do a lot of physics, but let's speak about the astronomy. What are the pros? The pros are the field is just getting started. We've had a lot of really fun results and discoveries over the past 5 years, but there's still a tremendous amount of discovery space, unexplored space that will get explored over the next 20, 30, 40 years. These new detectors coming up in the late 30s, the space-based ones, the ground-based ones, are surely going to deliver more compelling science. And again, there's so many opportunities to do different kinds of sort of sub-science in gravitational waves. Like I say, you can be a laser physicist, you can you can do numerical general relativity, you can work on machine learning. There are really many different domains here. A lot of what we do, the engineers that work with LIGO are super, and we owe a lot of the success of LIGO to the engineers who work there. So that I think those are pros. One, there's lots of opportunities and lots of different sub-disciplines that one can get involved in. What are the cons? One con is that it's both a pro and a con. The detectors are organized, or the detectors work through collaborations. All right, so the LIGO scientific collaboration, which I'm a member of, has now about 1,400 people. Virgo, the other detector I talked about, they have about 700 people, and there are other detectors that are coming up. So these are this is big science, and as a consequence, there's a lot of different parts of it that you never see if you're working in one particular field of it, and sort of getting noticed in crowds like that can be somewhat challenging. I mean, there are many examples of success of students who started as either undergraduates or graduates in the gravitational wave collaborations, and are now full professors and won prizes and things like that. So there are opportunities, but you are working in a kind of a different environment, and it's a more structured environment. I'll say it that way. On the other hand, our data is public. It's not public immediately, but you can download the data from all of our runs, and you can look for gravitational wave signals yourself. And we actually have schools that we run once a year, excuse me, that train students and things like that. So you can actually do very good gravitational wave science without actually being part of the collaboration. So I would say on balance, there's many more pros than cons, but like anything, you've got to look at the whole picture.
Great. Okay, and at least the final listed question here is there something fundamentally different about how gravitational waves look in the detectors, i.e. LIGO, that helps distinguish detection events from background noise?
Yeah, exactly. That's that. So the the signals that we look for, at least many of the signals that we look for, we know them in advance. So we start with the belief in general relativity, that objects who are orbiting around one another obey general relativity. That allows us, and it turns out there's lots of work over 30, 40, 50 years, maybe even longer, that is very theoretical, that actually allows one to calculate what these waveforms should actually look like theoretically. So we start from that, and then we basically say, okay, each waveform will look, they're all what we call self-similar, in the sense that the waveforms basically have the same qualitative characteristics. The frequencies will change if you change the masses. The phase, but the phase relationship sort of remains the same. So you can then use basically interpolation, computers and things like that to generate hundreds of thousands of these different waveforms for different kinds of black holes or neutron stars. And we do this thing called match filtering. So these waveforms that are computer generated, we call them templates, and we sift through the data using something called cross correlation. I showed it in an earlier slide. I won't go back to it, but basically we take the real data and we time slide. We basically take the template waveform, and we do a mathematical operation called a cross correlation, which as a function of time, where we time slide the templated signal against the real detector data stream. And when there's a weak signal or even a strong signal embedded in the waveform, as the time delay between the template and the real signal goes to zero, in other words, they perfectly overlap, you get a huge spike. All right, and that tells you that you've got a real signal. Now you need to see that in both interferometers. If you only see the one and not the other, you can't do it. You call that a gravitational wave. There's also we actually have a way of doing backgrounds, which I won't go into, but you can assign something called a false alarm rate. We can't, we make probabilistic detection statements. We basically say that this event has a false alarm rate of 1 in a million years or 1 in 2 million years, things like that. So there are lots of different, very understood, very tried and true methods used based on match filtering, based on statistical analysis of background events that allow you to make the detections. But it becomes more complicated for signals that we don't understand. Remember, I showed a picture of a question mark. If we get a weird signal, we can't use templates because we don't have templates. So then it becomes a little more complicated to actually, understand what we're seeing. There has to be coincidence. We have to know that the detector was not producing any spurious noises internally, but it becomes more complicated.
That's the last of the list of questions. I had a short question of my own, actually. I think back in one of the images you showed, it was of the LIGO detector, and basically you set the lengths of the arms, the difference, such that you get, like, I think it was a destructive interference pattern towards the end, and you look for deviations from that to detect gravitational waves. Was there a particular reason why, like, the length of the arms weren't set to be so that it was constructively interferent?
Well, we want the detectors, we want as little light to be hitting the output photodetector, that was that sort of black square that I showed in the movie, as possible, because any light that's hitting the detector that's not from gravitational waves is noise. All right, and it turns out there is some light hitting the detector. It has to do with some of the fact that the optics isn't perfect, things like that. But you want to minimize the amount of light hitting the detector because it produces excess noise in the electronics and things like that. So you set the arm lengths so that you don't operate. Actually, this is a subtlety, but we don't operate exactly on what we call a dark fringe. In other words, completely right at right in the well of that interference pattern. We actually shift the mirror off a bit. Actually, in terms of physical numbers, it's interesting to contemplate. We calibrate these detectors exquisitely, so we can move a mirror by 1 picometer, right? a trillionth of a meter. So we actually offset one arm relative to the other by about 15 picometers, and that lets a little bit of light into the photodiode, not enough to compromise the noise. But what it does do is when the gravitational wave pattern comes, it modulates the signal so-called linearly instead of quadratically, which you would get on a dark fringe. So you know, to wrap up, we're not completely dark, but there are reasons that you want to be as dark as possible for basically noise performance.
Let's see, okay. Okay, so if there's no more questions, I'd like to thank Dr. Reitzy for coming and giving a phenomenal talk today. The events tomorrow, we have, I believe, at 6:30, we have an astrophotography workshop given by Katerina Isabel Benavides. There's the schedule. And at 8 o'clock, sorry, that's at 8 o'clock. And at 6:30, we have the ethics panel with professors Dr. Jessica Dempsey, Dr. Robert McLaren, Dr. Heidi Nelson, and Dr. Shannon Pete. And then, weather permitting, we'll have an online observation time through our local observatory. Okay. I believe that will be all. So again, thank you much for coming. That was a phenomenal talk. Both of our talks were exceptional. Thank you again for coming out, giving your time. Sorry. Thank you all. Thank you, audience, for thanks to audience for coming out. We hope to see you tomorrow and on Saturday. And obviously, thank you to the organizers and to other fellow ASX executives coming out. Again, don't forget, there is a raffle. I think earlier in the chat, Julie, who is now gone, gave a link where you can purchase raffle tickets. But again, obviously, any ticket you bought for this event is good through the other two events. So if you're already registered, you can come to any future events tomorrow through Saturday. Great. Thank you very much, everyone.